Yes. So you can close that with anything else. Which one? Something popping up. I don't think it's the same. Hey guys, you able to hear me? Okay. Here. There? Yeah. Uh, so I'm going to talk about concurrency versus parallelism today, and we'll see how concurrency is, how it's different from parallelism and how it is not parallel. And we'll go through some Python examples. It won't be like a high level talk as the previous one. It'll be pretty low level, pretty ground up from showing a few of the Python code. Yeah, let's jump in. Yeah, before going to that, a bit about me. I'm Naren. I work as a product engineer in Mastery, primarily focusing on scaling backend systems and infras. And that's how my day looks like. Usually, I'll be sitting in dog corner and coding, or I'll be out cycling. If I'm not doing both, I'll be treating myself with good food. I love coding in Python, Golang. I'll be doing cycling and travel as my hobbies. You can follow me in Twitter. I'm insanely active there and occasionally active in GitHub. And that's my website and blog. Before going to the talk, let's have a quick count. How many of you have written concurrent production code?
I think I
Okay. Most of the code is executed concurrently, more or less by your OS, but still. Um, and how many of you have written Python in production? How many of you know about Python? That is basics. Yeah, cool. Again, we must go back to the basics to know what is concurrency and parallelism. Let's start with synchronous versus asynchronous. Everyone should know here what synchronous and asynchronous is. So I'm just going to rush through it. Synchronous is nothing but you'll be waiting for the response. If a task is doing if a process is doing some task and it is dependent on other process like web server or database, it sends a request and waits for it to respond, and there will be a blocking time. And asynchronous, there is no blocking time. You just if your process is dependent on some other web server, you send a request and you just continue the execution flow. Then on the fly you pick up the response. That's what asynchronous is. There is no blocking call involved. A very simple example of synchronous or synchronous blocking call is timed or sleep. And what's concurrent and parallel? So first we talk about parallelism. Parallelism is nothing but assigning different physical resources for your process or tasks. It might be separate memory, separate CPU cores, and you have task 1 and task 2, both will start together and execute parallelly in their own space. And in concurrency, it's totally about structuring the flow of your execution. So task 1 and task 2 might start at the same time, but it might not complete at the same time, and it will be sharing the same physical resource sometimes. And what happens here is task 1 will execute for some certain time, and when there is a blocking call happening over there, the control flow will switches back to task 2, it will start task 2, and when the blocking call happens in task 2, it will switch back to task 1 and continue task 1. So concurrency is about kind of parallelism but structuring your execution. We'll take a real world example. Who's running the same board? Yeah. So this is Olympic track or racing circuit, whatever we call it. You can see there are only about 8 to 9 tracks and 8 runners. Let's say 8 tracks and 8 runners. Does that mean only 8 runners can participate in Olympic event? No, right? There will be many of the runners waiting in the queue, and this is parallelism. You have only 8 tasks, 8 tracks, which are nothing. You can compare them to your CPU cores, and 8 tasks are your runners. Each is assigned to their own track, and they have to run in their own track. But if you take the other runners who are waiting there, they may not be mostly idle. Either they'll be stretching themselves or doing some other work, getting advice from their coach or whatever. And there will be someone called race coordinator who will assign the runners in the wait list with a bib number and the task track. Oh my God, I'm confusing with tasks and tracks. Track IDs, so that the runner can come out from the queue and they, you know, run in their own tracks. So that is concurrency. Recap: blocking calls, non-blocking, sync casing. Concurrency is making progress together and making progress parallel, literally parallel as parallelism. So we'll take another example to know how concurrency is not parallelism. What is this? I don't know. Dosa. Okay. Uh, can you move the mouse pointer? Uh, it's mine. Oh, I think I have OC. Okay. Yeah. So, she already said Sarana Bhavan's dosa. Let's assume Sarana Bhavan as one of the good hotel that gives you good dosa, cooks you good dosa. And the owner of Sarana Bhavan comes to you and says, "Hey, let's I see something in you. I'm gonna give you some money and start your own franchise in your area." As usual, you start small with a one chef and a one waiter. So a customer appears. What happens here? You have one waiter. You can go get the menu, and one chef go. The waiter can go and give the menu to the chef. He can cook it and give back the dish. You make the customer happy, and that customer brings more friends. Hey, we got a good dosa here in our area, and let's go check it out. And you have 3 customers at a given time, and unfortunately, 3 of them has different requirements or want different food. So what happens here? You can serve 3 customers with your one penguin, not penguin, waiter, and a chef, but still it won't be as easy or as quick as serving one customer, right? So you're thinking of that and you say, okay, at any given time I'm getting 3 customers, so let me increase the number of waiters. Then you realize, oh my God, Jeff is alone cooking in the kitchen and he can't handle many orders, at least 3 orders at any given time, and you increase your resources. So this works well for 3 customers, and suddenly your hotel becomes so popular. At any given time, 10 to 20 customers appear, and you follow the same way. You increase your resources, throw your resources on the problem. Will it solve? No, because it is kind of parallel, but you are there are 2 things. What if it's a dry day and there are no customers? You will be paying all your laborers or your waiters and your I should not call laborers employees and your chefs. So you have to pay them for their idle time. And if you take the kitchen might have only specific set of resources like similar to gas burners or ovens. But if you dump more chefs into the kitchen, it is not going to solve the problem. It will be so messy, and you need to again increase your resources. So this shows you can't just throw your resources to solve the problem. You have to structure them. This is how you do it. When you have customers, you ask them to wait in a queue, and you have 3 to 4 waiters. And when one is picking up the order, other will be telling his order to the passing his order to the chef, and it will be waiting in the queue, which has to be cooked. And if you take this model, I mean, right now you would have got right how parallelism works and how concurrency works. Yeah, any questions? No. If you take this model, you just assume the chips are your cores, CPU cores. These are your requests, HTTP requests, and the queues are nothing but a network channels or something, and these are your web servers behind ENV. Does that make sense? That's how you design something, right? Yeah. So we saw what is concurrency and what's parallelism, and we took a real world example and saw how concurrency is not parallelism, how it's sometimes how it's better than parallelism. And let's talk about concurrency in Python 3. Async IO is the standard library in Python 3 with which we can. Is that okay? So yeah, it's a standard library in Python 3 through which you can write model your code, your concurrent code, and execute them concurrently. So it was introduced in Python 3.4, and it's totally inspired from a library called Twisted, which was already there in Python 2.x versions. And right now, the latest version is Python 3.6. It's heavily improved and it's more fast now. Let's when it comes to async IO, these are the three things you have to remember. Async IO in Python 3: event loops, coroutines, and futures. So event loop is nothing but your manager. So remember the race analogy that I gave you. There will be a race coordinator who will select the athletes and assign them tracks, right? That's more or less similar to the event loop here. And it manages and distributes the executions, and it is responsible for registering the tasks and distributing the flow of control between them. And coroutines are nothing but your normal methods in your Python, but they have a special capability. They can release back the control flow to the event flow. So whenever whenever a coroutine is blocked by IO, we can give back the control flow to the event loop so that it can execute event loop, can execute the next coroutine. And futures are nothing but the objects. It's just a type. It's the type of the object which you feed into the event loop to get executed. And the objects may be sometimes exceptions or completed tasks or pending tasks. So let's see how concurrent program executes in Python. So we spoke about event loop, which is the manager. We spoke about the coroutines, your methods, returning back the control flow to the event loop, and the features are the tasks. We have a thread. In Python, your asynchronous program runs in a single thread. And event loop will be getting the tasks from the queue. Is it visible? The back? Okay, I think I can't zoom it. I already tried that. Event loop will be executing the or getting the task from the queue, and when it picks up the first task, it will run the coroutine one, which is the method associated with that task. Then, while coroutine one is running, it sees whether there is some blocking call, which is IO blocking or sleep or whatever. If there is a blocking call, it gives back the control flow to the event loop, and the event loop will pick up the task loop. This happens until the this box here it repeats for every task in the queue. If there is no blocking call, the control flow the program continues its flow, and the tasks get completed and next task will be picked up from the queue. Coroutines are the methods which execute the task. Add might be a coroutine, and subtract might be a coroutine, but a task in this example both are same. The task and the coroutine is same, but coroutine you can assume it's a method. So it can be like this: addition is the task, add is the method, which is the coroutine. Yeah. So I have few code examples. I'm going to show you running the code examples and show you how to design a very basic concurrent program in Python 3. Try not to sleep. I don't have memes anymore. Let's dive deep into concurrency.
One small question.
Yes.
So the concurrency that we are talking about, is it with respect to the HTTP request, or is it with respect to the amount of usage you are having on a particular code you are using?
No, it's totally, sure mentioned that it's totally about the I/O blockings.
Okay.
So when you use concurrencies, if your code is heavily I/O based and it has depends on a database or opens multiple files or handles web servers, sockets are nothing but the files open by your kernel. So in that case, we'll be using it's good to use a concurrent program where when there is I/O block, the control flow switches. Have any other questions?
Seems very similar to Node.js. What Node.js is doing.
Yes.
Right?
Yes. Let's go to the console or my ID. Yeah. Yes. Python is no, everything is a sequential program. Not all languages. Most of the languages are sequential.
Can you increase the font size?
Yeah, sure. Is it visible on the back? Yeah. Okay. So I was talking about the context switch, right? How tasks get executed, and when I/O block happens there, it gives the context back to the event loop, and it switches back to task two. Let's see that through the code. So I have imported async I/O, which is standard library I'm going to use, and I have defined most of them here knows Python. So I have defined a method, but I have prepared it with something called async, which make this a coroutine, in which in turn is available. I mean, capable of returning the control flow back to the event loop. So we have basically defined a coroutine here, and it just prints the start method, sorry, start statement, and the keyword I am using await, right? Await, it is the line where the control flow is given back to the event loop. So whenever you use the keyword await, you are saying that you can get back there is something going to happen with the blocking, or a blocking call might happen, or something with the IO block. You can give back the control flow to the event loop. So here you know that you're going to do a sleep for 5 seconds, which is a blocking call, and you're using await and giving back the control flow. Similarly, in coroutine 2, it is doing the same, using await async.sleep, and you're printing the starting and ending of the method. So here you're getting the event loop object from async IO, and you're creating the tasks. You're creating the features. So when you wrap up the normal method or coroutine with this IO loop to create task, it will become a feature object, and you're combining them So just combining them into a list, which is basically a queue of this line, and next you are uh, combine them into using async IO.wait, then feed it into your event loop. Then once it gets executed, you're closing the event loop. Let's see what happens when I run this. So it started task 1, and if it's sequential, you should have printed this statement, right? You should have waited for some time and printed. But here, the context switch happened, and it control flow went back to the event loop, and the event loop took the next task in the queue, and it started the next task. Then it printed started task 2 after context switch. Again, await happens, and the control flow is given back to the event loop. Then it looks for the next task, but there are no next tasks, only 2 tasks, and get back to the task 1 where it's paused and it executed. Then once it gets completed, it looks for the next task, which is remaining the only task. Then it gets executed. So this is a very basic example of using writing a concurrent program in Python and how the context switch happens. Do you have any questions on that?
So the event loop, in this example, you manage it within this
Yeah.
example. But on an application level, on how do you manage that? If you have an application, each application has its own event loop, and what patterns do you use to manage that?
Mostly you can abstract the code, but it depends on your use case in applications. Can you give me some specific example?
So no, my question is towards like you have an event loop for this set of operations.
Yes.
No, I have a much bigger application which has many operations.
Okay.
Do you manage that event loop for all those operations, or do you have separate event loops for different set of operations?
You can logically group your operations, and you can have separate event loops too.
Okay, because the reason I'm asking is because this is very similar to what we do in C#, async await, right? But we don't manage the event loop in C#.
Okay.
That's basically, it's not, they don't call it concurrent programming, they call it asynchronous programming. But the concept is more or less the same.
Okay.
So I was just wondering, since event loop you're managing starting and stopping and running the tasks, so if you're free to do that, you can do that on small scale, a large scale, or you can use multiple event loops within your application. That's possible, right? Can you use
that's possible. You can even run the event loop in a single thread or a separate thread or mostly separate thread. Then you can feed the task to a queue to that thread, something like that.
So what is my I have a database.
Okay.
Actually allow me to take the thing or something.
Okay.
So what if one of the API does not support
I was about to talk about, was about to tell about that, but still,
yeah, so
one thing you noticed, I don't know whether you noticed here, I use async IO.sleep, but generally in Python it's just time.sleep or something like that. So what time.sleep does is it will sleep for 5 seconds. That is a blocking call, but it is not capable of returning the control flow back to the event loop. So I am using some a special different library, or which has the capable of async programming, and there are a few libraries which will support asynchronous programming or compatible with async IO. If you are using other libraries, you can do something called import from concurrent from futures import concurrency or something. So it will wrap up your from concurrency import futures, which means you can wrap your normal libraries into a future. The future is type which you can feed into async or event. Does that answer your question?
we need to wrap it up.
If it's not available as this library. But most of the libraries are now it's available. It's compatible with basic IO.
But C sharp is the same, right? You have to be async from the top to the bottom.
Otherwise, you need to put it.
Otherwise, you need to what? So what you're saying import concurrency from. What we do is we wrap that non-asynchronous operation in the task object.
So I don't know much about C sharp.
No,
C
but
sharp,
the
is it
concept
was
is the same.
concurrent from the beginning or it was introduced in some
No,
other?
it was not. I should say it's in point 4.0, 4.5.
So yeah, that's the issue. Even Python it was introduced in 3.x. And if you take Go language, it was built with concurrency in mind. So there it will be much more efficient and it will be much more faster. I don't know that. So since they introduced in
Node.js, basically everything is concurrent. Any call, everything is concurrent. So everything is concurrent.
So Node.js is very similar to twisted library from Python. So one of the, if you see some of the talks from the Node.js guy, twisted library from Python is one of the inspirations that we have.
okay.
Because twisted is, I think, one of the oldest libraries that is doing async IO for a long time.
Mm. Features. So yeah. So like the future is studying by the type of the task which the event loop will take in. So you're just wrapping up your normal coroutine with by using to create task and it becomes it will return a future. No, we are doing it.
I have a question.
Yes.
So let's take a case. Let's take a case where I have written a Python application where I have a listener
Okay.
which is sort of listening to a tube, and if there's any message coming, it's going to take a process. And meanwhile, in the same environment, I have some other process also running.
Okay.
So my question is logically, since Python is a single-threaded application, without implementing this, async, um, can I have this listener separately working and this, some other yet another process working separately? Is it possible? Or
without async.
yeah, because even if I have async, then I can have a control like on the listener when I get the message, I'm going to take the control and after processing it, when I'm going to wait for the next message, I will say okay, I'm waiting, give the control back to the other process. I can do that. But generally, if it's going to be one listener, then it's fine. But in a typical enterprise application, you will keep on writing n number of listeners and a lot of stuff, right? So you can't keep on releasing your resource, right? So what? So in such a case, what I assume is the language by itself should take care of this sort of. I would say this is actually a time slicing concept, right? So
yes.
The language itself should take care of time slicing, right? So my question is, does Python really support time slicing or?
No, actually you can't. Everything is almost single threaded in Python since there is GAL, and it's not truly multi-threaded, at least in Python.
No, multi-threaded is different. I agree. So no, the point here is a language by definition. I believe it should support time slicing because if we write a code like this, we are taking the time slicing. Right? When I say time slicing, it's like I'm processing certain tasks. I'm free now, so let this CPU used by some other task. So the time slicing basically any language will use the operating system time slicing concept. So for example, Java, even C# use that.
Yeah.
But why do I need to explicitly mention those kind of time slicing here?
Because you are the one who writing the code and you know where the blocking call is. You will know.
Okay, so if I don't give that, then it won't happen, right? That's
usually it will take, if you use multi-threading instead of this, mostly OS will handle the time slicing or interleaving, and it won't be as you won't get the fine grain control as you do in ASIC. So we go to the next example, which is similar to the context switch. Here we are importing time and async IO, then we're just uh, measuring benchmarking the code. And the task one, which is coroutine, we have we are doing just the similar thing as in previous example, but we have three tasks and we are sleeping, doing async IO or sleep for different amount of time. We are combining the features and putting it into the event flow. Let's run this. So task one got started the work, and same as the previous example, it was a blocking call, and task 2 started, and even it can't complete since it's a blocking call, and task 3 kicked off. But if you notice something, task 3 has finished first. Can you guess?
Yeah, because the time.
Yeah, because the amount of the time at which the blocking call happens. And this shows that there cannot be an order maintained in asynchronous programming, which comes to the next example. And here we are sleeping for a random amount of time. So we have a synchronous task, which will sleep for a random amount of time and print when the task is done. And we have the same asynchronous task using async IO or sleep, and we are initializing 10 tasks synchronously and asynchronously. Then we'll execute the synchronous task first and next the asynchronous tasks. So this clearly shows the difference between the synchronous and the asynchronous, right? So each task is getting executed one by one by when you're running it synchronously, and here if you take it totally depends upon the time at which your blocking call happens. And let's talk about some real code example or real use case where we'll implement, we'll do some HTTP calls using synchronous as well as asynchronous. We are importing requests and time and async IO and AIO HTTP. As I said, you need to have a special library to make it asynchronous. So instead of using normal HTTP library or request, I'm importing AIO HTTP. I'm hitting a server, which is a gaming server, Battlefield 4. So how many of you are gamers here? Oh wow. Okay. So first I was hitting a GitHub server, they blocked me, and these guys seem so generous. I'm hitting the Battlefield server for 3 times, and I'm making a synchronous HTTP call using uh, request module and just passing some random key from the header. Then I'm doing the same using by doing asynchronous call. So here I'm using the keyword await, right? At this line, I know that if I make a call to some server, that is a block. It's a blocking call. But the response totally depends upon the latency of the server. It might take few seconds or few milliseconds or even few seconds or few minutes depending on the load of the server. So here I use the keyword await and I am returning back the control flow to the event loop. So we are kicking off, we are initializing the tasks and asynchronous tasks here. Then, as usual, we fill it into the event loop. So the synchronous process has started, and it took like 1.34 seconds for every call. Right, we made 3 calls to the server, and if you take the asynchronous, the all 3 process started. Like if you see, the first process started and it was waiting for the server to respond, then it printed the output of the process. But here it wasn't waiting, it started the consecutive process. And if you notice, the total process took only 1.12 seconds, which is the maximum waiting time of one of the tasks. So, and you ignore these errors due to some incompatibility issues. And it's just similarly you are trying to create concurrency. It is more or less similar to previous example. Yeah.
So the place where you are making the HTTP call,
Yes.
that's call.
Yeah.
So when it sees the await, it's like goes to the event loop, right?
Yes.
So who is actually making the call? Which
It's a single thread, and it's just the event loop. It's just a callback. Callback to the event loop. It will say that a blocking call has been happened, and event loop will just try to take the next task.
Yeah. So the call has to be made from some thread, right? So it actually makes the call, and then it goes to the event loop, and the next task gets executed.
It's in Python, since it's single threaded. It will make the call, and it is not like the control flow gets switched, but still here we'll be waiting for the response. So what you're asking is why there is no multi-threading, or how it's handled in single thread, right?
No, the function that's on the same line as like of await. So which thread is executing that function actually? That's an issue.
Which thread is executing that function?
Yeah. So it's a single thread. So before going to the event loop, it's getting triggered like or executed, and it's going to the
Yeah, before getting to the event loop, it's getting triggered. Then it's verifying the event loop, and meanwhile it's waiting. The event loop is executing the next task.
And what if the function that I given the await itself has another await? Let's say task 1 await is calling task 2.
That's so meta. I don't like that.
No, but basically, let me go to the event.
Yeah.
Event loop
Yeah.
will decide. I mean, what it will be.
Yes.
Okay.
Sorry? No, I'm not aware of JavaScript. I know what a promise is, but it's more or less similar to promises. So what you asked might be when the first await happens, the first event loop will take care of that, and second await happens, maybe the second event loop will take care of that. I should try that. So, any other questions so far? No. And we just ran a very similar code here, which did to the request to the same server, and it took the whole process took 5.97 seconds, which is the maximum amount of time to play one of the tasks. Let's see something called return event. So if you take this use case, we need to find our own IP address, which is find my IP. We use different two services called IP5 and IP API. And we try to hit that and we get the IP. But the difference is here, all the task is going to return the same result for us. So it's not necessary that we have to wait until all the tasks to get completed. So whatever tasks get executed first, we are happy with that, and we will terminate the event loop. And we have a coroutine here, and we'll do a get request and pass and print it. The only difference is it's done there. When we queue it when we combine the tasks using async or await, we are mentioning that return when equal to first completed, which means the the event loop it will stop executing when the one of the first task or the task which gets completed first. So right after we get an IP address from one of the tasks, which is the fastest server going to respond, we are terminating the event loop. So I'm running this example. So the API was able to, we were able to hit the API and we were able to find our IP address, but we got some error, which is task was destroyed, but it is pending, which means we didn't stop our event loop gracefully. Let's see something called cancel future, which allows us to stop or cancel the other pending futures. This example is very similar to the previous one, but here we are looping through the futures, which are our tasks, and here we are doing future or cancel. So when you do async or wait, it returns a list of pending futures. So what you iterate through the pending features and you do cancel, so that you are cancelling your pending features and basically closing your event loop. When you run this example, you shouldn't throw that specific error. And handling exceptions are very similar to your normal code. Here, when we are making requests to a different server, we are just using try except as usual and handling the exceptions. It's nothing much in that. And we see about something called wait timeout. So here you have what if the server which you are trying to hit it has a very large latency. Like you can't be waiting for a very long time, right? If you are waiting, all your tasks will be in pending state, and the event loop won't get closed until it's all the tasks are getting completed. So here we'll have something called timeout, and we will include that timeout in the async IO wait clause. So let's see what happens when we run this. So it waited for 0.5 seconds for the server to return, and the server took just 2.29 seconds, which might be the internet latency as well as the server's response time. We'll reduce it to 0.1 second. So we waited. See here, we didn't get the IP, which means the server took more time than our wait timeout, and we didn't wait for the server to respond, and we closed the event loop even before that. So these are some basic, snippets with which you can write. We wrote the concurrent programs in Python, and let's take a look at the screencast. Here I used before that I show you the code. I just I was hitting the same battlefield for server for like 1,000 times or 500 times, and I took the response and I opened a file for each response, and I wrote the response into a file just as a plain text file. I did it parallelly as well as I did it concurrently, which means while doing it concurrently, I used async IO files, which will support concurrency instead of normal files library in Python. and let's see the comparison how it went or the benchmark. That's the cores in my CPU. This is this laptop, and I'm making the parallel HTTP call. So you can see the cores in peak, like away from the starting of the execution to the ending of the code. All the cores are replaced to 100%, just to make few API, like thousands of API calls to a server. And the total time taken is 13.99 seconds to make thousands or 500 API calls. It's 500, yeah. And I'm running the similar code concurrently, or concurrent version of the similar code. Look at the utilization and code. There aren't any, it's not getting utilized for 100%. And there might be some spikes, it might be due to number of files opened or something, but you can still see the difference, right? When you run the same code concurrently, it didn't take, when it was taking the 100% of your course all the time, and when you ran it, sorry, when you ran it parallel, it took all the course, and when you ran it concurrently, it was just not as bad as your parallel code. And one thing to notice here is it took 14.54 seconds, which is very close to your parallel code. And when you ran the parallel code, you used all four of your processors, but here you used single threaded a single processor. Since it's Python, you're using it's a single thread and you're using only single core of your processor. But to take some other language, concurrent language like Go, you'll be using multi threads as well as multiple processors, and you can imagine how fast it will be. Yes. Uh, yeah, but there is a spike, but there are no, like it's not being replaced 100%, right? Maybe I don't know about the spike. It might be due to we are opening multiple files and the context which is happening back and forth for like hundreds of times. And
So async could be a right solution only if there is
IO
intensive operation.
Yes.
If there is going to be a CPU intensive operation, async will not work.
we have to go for multi-processing, compute intensive, or and how concurrency different from multi-threading we already discussed. In threading, your OS will try to handle the context switch, and it may not be right all the time. And in async, you will have the pretty good control of the context switch. Yeah. Summary: sync, async, concurrency, parallelism, and use Python 3 async IO, AO HTTP for HTTP calls, and AO files. These are some things some code examples we saw, like how we saw about wait timeout, and we had a mention about parallel and concurrent calls, and how to cancel a pending feature to basically shut down your or close the event loop. And I'm out of bullet points. Any questions? Thank you guys. You did not sleep. I was showing like totally only code and text files. So I think you guys answered most of the questions. You can find the slides, code examples here in this URL bit.ly/concurrency versus parallelism, and you can find the other slides or other talks in my website. You can ping me through Twitter, this handle, if you have any doubts or if you have any issues with regarding this talk, feedbacks, anything. Thank you. Now we can
Quick time check. It's almost 8:30. So we have another talk which will take another 30 to 45 minutes. Is it okay to have it now, or you want to postpone to some other day? So how many are okay with having it now? Then we'll have it.